Assalamualaikum. Good morning. Assalamualaikum. Good morning.
Good morning, Doctor.
Dengar?
Dengar.
Okay, alright. Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh and very good morning. Today is Saturday, 23rd of January 2021. Okay, so let's move to the next chapter, which is chapter 4, Mkem1763, under the title of Parameter Estimations, where previously we learned about how to conduct experiment with a specific input signal, okay? For example, sine wave, PRBS, step, impulse, and so on. Then after that, we learn about model structure selections. And then now we are going to the parameter estimations, where we are going to see what is the method that we use to estimate the parameter of the mathematical model that we achieve. Basically, the concept is shown in this picture, where you have excitation signals, okay? Sorry. Then you have a digital to analog converter for data collections. Okay, into the plant, where the analog signal will be injected to the plant. And then the output will be captured by analog to digital converter. And this analog signal and the output, okay, will be interfaced to the computer, where we allocate the identifier algorithms, okay, to estimate the coefficients of the parameter model. And finally, we get the model. So there is a lot of discussions, a lot of debate, and a lot of changing ideas between the analytical model and empirical model. More or less, the target, the vision is the same, where we're going to find the parsimonious model, the best model that represent the unknown system, okay? So how do we obtain the transfer functions empirically? Okay, so Albert Einstein, okay, give a opinion that any intelligent fool can make things bigger, more complex, and more violent. It takes a touch of genius and a lot of courage to move in the opposite directions. So system ID is an alternative way for opposite directions instead of analytical model, where we use for the forward modeling. Okay, we derive from the first principle, but sometimes we must have a courage and we must have a knowledge, and then we must dare to test in the opposite way by taking the experiments, by doing the experiments, take the data, and then you construct the mathematical model based on the will help from the computer nowadays. So a good model is not obtained by accident, but it requires a careful planning and execution of the essential steps. So you must have the 4 steps, which is the experimental setup for data capture, and then model structure selections, and then the parameter estimations, and then the validations of the model that we get in order to achieve the best model that we can get. So this is the setup, okay, in order to do the data collections and for the parameter estimations. Okay, so basically this is the important, what do you call that? The important engine of the setup, which is the identifier algorithms. So there's so many algorithms proposed, okay, in the book, Okay, so we are not going to touch everything. We just select 2 or 3 in order to obtain the mathematical model. So as I told you before, the paradigm is shown here, 1, 2, 3, 4. From the beginning to the end, you must have these 4, especially in the assignment as well. Okay, you have 1, 2, 3, 4 as well. Okay, in order to validate the model from your assignment, which is consumed of 30%. So the assignment will be, due date will be on the next week, Saturday and Sunday. Saturday is for your presentations. Then I will make some comments, then you improve via corrections, and then you submit final version on Sunday next week, okay, next weekend. So, for example, if we want to test a simple motor, okay, as shown here, connected with the power amplifier. So first of all, we must have the input VI, okay? And then this VI will go to the power amp, okay, to increase the amplitude and the power of the signals, and then injected to the motor, okay? For example, this is a DC motor. And the output of the DC motor is the speed, where the tachometer, okay, the tachometer will convert the revolution per minute, RPM, of the motor, okay, and convert this RPM, the physical signals of the velocity of the DC motor, towards the voltage, equivalent voltage, okay. So in this case, okay, you can see that the motor, which is considered as a first order system with a sampling period 0.50 milliseconds, okay? So we have to estimate, okay, the numbers here, 3.77041 and minus 0.192, okay, in order to get the mathematical model. So this is what we call as the parameter, 3.771 minus 0.192, okay? The signals that we use is step input, and this step input will be multiplied with the system in order to find the response, which is a YQ. And in order to do that, we must have data collections like this. Okay, at sequence 0, what is the input, what is the output? At sequence 1, 1, and 3.7. What at sequence 2, the input is still 1, but the output is 4.49. So this data is very important in order to do the parameter estimations and in order to get this final pH, okay, the transfer functions of the mathematical model, which is known as a first order system. So parameter estimation is an effort to seeking to find the best values for a given parameterizations and selected appropriate cost functions to minimize. And then this high cost is not good, while low cost is good. This is a case as a standard optimization problem. Okay, sometimes the higher order of the system sometimes is not accurate compared to the low order of the system, because the higher order system sometimes have a poles and zero, which is very near together and can be cancelled out if we want to reduce the mathematical model order. So this is what we call as a standard optimization problem using a least square and can be solved. So the block diagram for the parameter identification is shown here, where you have a real system over here, okay, and the model. Okay, so we are proposing the model that is near and equivalent to the real system by taking the input output. Okay, for example, we give the same input to the real system, at the same time we give the same input to the model, and then we compare the output. Okay, where this one is the real system, which is known as Y, and the model output is known as Y cap. Y cap meaning that is the estimations, okay? Y cap, let me write for you. So this is Y output, and this is a Y cap, okay? So the output error will be the modulus difference between the Y, the actual Y, and the Y cap. That is represent the error, okay? So this error will go to as a quality factor. The smaller it is, the high quality it is, the bigger it is, so the bad of the quality factor. And this quality factor will go to the parameter estimations, okay, process, okay, and then we will be submitted to the model, okay, which is the nearest one that equivalent to the real system. So parameter estimations provide a mean of estimating the parameters directly from the data. That's why you must have an input, and you must have the actual input and actual output. Okay, this output will be compared together, which will give you the prediction error, which is E. And this error will be feedback to the models, okay, and will give the final, is a recursive process, is a looping process that will be finalized after the coefficient is get the unchanged value that represent the model. Typical applications of parameter estimation, including in monitoring, in machine learning, noise cancellations, in vibrations, forecastings, and other. So those who are graduate and pass this subject, inshallah, be able to do predictions, okay, based on the scientific data, okay. There is a lot of people can do predictions, okay, without scientific data. Okay? This one is, so for example, fortune teller, Bomo, they predict the future, but they are not based on scientific data. They are based on their imaginations, okay? But scientifically, as an engineer, as a postgraduate students, they can predict, okay, what is the future based on the scientific data. So the data is vital and important as the tools, okay, to be inserted in the identifier algorithms, and then we can predict what will happen next. So least square estimator is one of the method in the identifier algorithms where we must have a input-output pairs, which is known as U and Y. Okay. So I is the sequence, you call it as the training data. Sometimes it is 100, sometimes it's 1,000, 2,000, and so on. So system ID needs to do both the structure and the parameter identifications repeatedly until satisfactory model is found. And this will follow as shown. First, we have to specify and parameterize a class of mathematical models representing the system to be identified. Okay, this is more towards the structure selections. And then we perform parameter identification to choose the parameters that best fit in the training data set. When we conduct validations to see if the model identified responds correctly to an unseen data set, and then we terminate the procedure once the result of the validation tests are satisfactory. So we usually use several methods for validation. The popular one is the best fit. For best fit theory is the best data. The best models is follow the data exactly, okay, on top of the data, meaning that if we have something like this, okay, this is your data, okay, right? So if you, where's the color? Okay, 100% best fit is the red line will follow the blue data from the experiment exactly, okay, like this, exactly. towards the data. The red line is the approximate. The blue line, the blue data is the real data, and the red will follow exactly the data. But if you have something like this, which is this data, okay. So this is your data, and then less than 100%, let's say 90% is like this, okay. Tries to follow the data exactly, but cannot follow, okay. So this one is considered as 90% from my based on my observations after so many times review and analyze the data. So the best one is 100%, okay. But the theory said that the best fit is greater and equal 90%. Okay, so that one can be accepted. If you achieve 70% best fit, so it's okay, but not accurate, but you can improve it by doing the model structure selection again, then by changing the identifier algorithm that more suitable, and redo the experiment, okay? So in general form, least square is can be represented by this equation. Y is equal to theta 1, f1 function of u, theta 2, f2 function of u, and so on, where okay, where u is the input, model input vector, f is the unknown function of u, okay, and theta 1 and theta n is the unknown parameter to be estimated, the parameters that need to be estimated. So the task is to fit the data using a linear model. It's referred as linear regressions, as I showed you before, for 100% and 90% best fit. So the model, the red line, which is the fit, try to fit the data as good as possible. That we call as the linear regressions. So we collect the data which is known as u and y, and the equation will become in the blue box, okay, which is equivalent to A theta y, okay, A theta y, where A is the f1 function of input until the final data, and then theta is the unknown parameter, and then y is the output, okay. So this is known as A theta y. So if we want theta as the title of the formula, so we have to bring A to the right, and A will become inverse A. Okay, so we know that A is the matrix, which is a data of the input and output. So when we use the least square estimator, so theta is equal to inverse AY. So we have to find inverse A. Okay, so usually we are using calculator or manual calculations. So we have the M outputs and N fitting parameters. So to find, okay, which is known as M equation and N unknown variables. So usually the M is greater than N, the order, okay, since the model is just an approximations of the target system, and the data observed might be corrupted. Therefore, an exact solution is not always possible. And to overcome this inherent conceptual problem, we introduce an error vector where E is added to compensate, okay, to compensate the corrupted data, okay, which is A theta plus E, which is equal to Y. Our goal is to find the theta or theta cap, okay. this one we call it theta cap or theta hat, the estimated parameters that reduce the error between yi, the actual y, and the estimated y. Okay, so therefore we have to minimize, okay, the actual y, okay, using the estimated y, which is ai t theta. Okay, you don't have to derive this. Okay, I just show the formula rather than to minimize square. Okay, so we have to use the modulus. Okay, the modulus. And then we sum it. Okay, so you don't need to square it. Okay, so if E is equal to y minus a theta, then the error will become y minus a theta transpose t. Well, power of t is transpose, which is the interchange between row and column, minus y a minus theta. So we need to compute this in order to find the parameters. So the theorem of least square is shown here. The squared error is minimized when theta is equal to estimated theta. We call it as the least square estimators that satisfy the normal equation A transpose A estimated theta equal to A transpose Y. So A transpose A is a non-singular, okay, meaning that the determinant is not equal to 0, non-singular. So theta cap is unique and is given by theta cap, which is equal to A transpose A. Both of them multiplied together, then do the inverse, multiplied by A transpose, multiplied by the output Y. For example, if you have a simple experiment between the spring length and the force applied, which is equal to K1F plus K0, which is known as a linear model. Okay, so we have to try to find the estimated parameters, which is theta cap. Okay, that fits the data for a given force F0. So we need to determine the corresponding spring length L0. So solution one is to provide two pair of data, which is L0 F0 and L1 F1, and solve a linear system of two equations and two variables to find K1 and K0. However, because of the noisy data, this solution is not reliable. So we have to use a larger training set, which is LI-FI. We have to collect the data. Okay. So we do the experiment. Experiment 1, 2, 3, 4, 5, 6, and 7, where each experiment have a different input force in Newton. So the first experiment, we give input 1.1 Newton. Then we obtain the length of the spring 1.5 inch, and we increase the force 1.9, 3.2, 4.4, 5.9, 7.4, 9.2. So basically we have 7 data input and 7 data output for the training data for the least square estimator. So since y is equal to E plus A theta, so we can write the data as shown here. Okay, so this is the A, okay, A, which is input 1111, okay, from experiment 1 to 7. Then this is the output 1.1, 1.9. And K0 and K1 is the estimated parameter, which is theta. Okay, so this one, okay, A theta. Then plus the E, okay, the compensate error, and then equal to the output, okay, 1.5, 2.1, 2.5, and so on. So therefore, the least square of K0, K1T, which minimize the equations shown here, is using A transpose A inverse, A transpose Y, which is known as 1.2 and 0.44. Okay. So we rely on this estimation because we have more data. Okay, but sometimes this spring have the limit. Okay, so this limit, if you give a more input, meaning that more force in Newton, so the model that we propose might be not accurate. Okay, for example, here we try a first order model structure. We select a first order model structure. You can see that the blue line try to fit the green data. The green data is the real data from the experiment, but not good enough. And second order polynomial is much better compared to the first order polynomials. Okay, and then the third third order model structure also good. Okay, and the fourth model also accepted. So which one is the best one? Okay, it's between the second and fourth. So we choose the third order that will represent the system. So as an introductory examples, we give you experimental data. So this data is about 1, 2, 3, 4, 5. 5 data of input and 5 data of output. Okay. So the hypothesis that we choose the model structure as the first order system. Okay, B1Q, 1 plus A1Q. So Q is the equivalent to the Z in the discrete form. Okay, some people using Z, especially in British books, they are using Z, but in US they're usually using Q. But both are the same. Okay, a discrete form, Laplace discrete operator. So we desired the values of A1 and B1. We want to estimate the A1 and the B1 that fit the data given. So we use the difference equation YK, which is minus A1 K minus 1 plus B1 U K minus 1. So we fit the equations as shown here. So going from K 1 to 4, we stack the equation as follow: Y1, Y2, Y3, and Y4, and minus A1, Y0, Y1, Y2, Y3, and B1, U0 until U3. Okay, then this will be equivalent to the minus Y and U and multiplied by A1 and B1. We factorize the A1 and B1 out from the equations. Okay, so this is known as the size of the matrix is 4 by 2. Okay, 4 row, 1, 2, 3, 4, 4 rows, 2 columns. So the size is 4, 2, and this one is 2 by 1. Okay, we have 2 rows and 1 column. So this one can be multiplied because the end and the front is 2. So it will give you a matrix of 4 multiplied by 1. Okay, which is here. Okay, so this is the matrix of 4 by 1. Okay. Then we use the y is equal to x theta. Okay, y is 2 minus 0.2, 1.82 minus 0.32 from the data, and then x is the input-output data. Then theta is the estimated parameters of A1 and B1. So we use a least square formula, which is theta x plus y, which is x transpose x inverse, x transpose y using a calculator. So we find x transpose x matrices, x transpose y, then theta, which is equivalent to 2, 1 minus 0.91. So we compare. So this is the A1. We look at there, B1 over 1 plus A1Q. So this is the A1 and B1. Okay. So So let's say we have a longer data, which is a 9, which is shown here, where input U and output Y. So see, the hypothesis is we choose the model structure selection as a second order system. Okay, B1Q plus B2Q square over 1 minus A1Q plus A2Q2 square. So we designate the values of A1, A2, B1, and B2. So we have a four estimated parameters that best fit the data given. So we use the difference equations of the second order system, which is here. Okay. Previously is the first order difference equation. Now is the second order difference equation because our structure is second order. Then we simplified from k equal to 2 to 9. Then we start the equations as shown here, right? So this is y, 1, 2, 3, 4, 5, 6, 7, 8. Okay, 8 by 1 matrices. This is 1, 2, 3, 4, 9 by 4 matrices, and then we have a 4 by 1, which is the estimated parameters A1, A2, B1, and B2. So we can write this as y is equal to x theta, where x transpose x, okay, by using a calculator, we get this value, that x transpose y. Then we optimize using a least square method, which is x transpose x inverse, x transpose y. Then we obtain the estimated parameters as shown here. So you can see that the A1 and A2, B1, and B2 is shown in the transfer function, which is compared to the, we call this model structure selection second order, okay? So let's go to the real one by calculating. So you are given a process model in the form of yk, b1, z minus 1, 1 plus a1, z minus 1 uk. And the data is given here, where k is equal, the sequence is 1, 2, 3, 4. Input u, you have a 4 input, which is commonly known as PRBS. 1 minus 1 minus 1, 1. Then y, 12, 4, minus 12, and minus 4. Estimate the parameters b1 and a1 using a simple least square. So given the process model is the form shown here, okay? Data is given, so you have to estimate the a1 and b1. So we have to write the first order difference equations, which is y k plus 1, which is equal to a 1 y k plus b 1 u k, right? So can we go to the sharing? Okay, here. So first we have to write the model in the form of y k plus 1 equal to a1 yk plus b1 uk, or in the matrix form y theta beta, okay, where beta is the a1 and b1. So how are we going to form the y matrix? Okay, so if you look here, okay, y is equal to 4 minus 12 and 4 minus 4. Okay, so you look at the equations here. Okay, you look at the equations here. Okay, so minus a1 yk. So we have to refer to the data given. Okay, So the data is here, okay? So minus A1 YK, okay? There is a minus here. So how we get 4 minus 12 and minus 4? Okay, simply from here. So this one is minus positive 4, minus 4, minus minus 12, positive 12, minus minus 4, positive 4. Okay, that's why you get 4 minus 12, okay, 4 minus 12 and 4 from the data, okay, directly from the data. And then for theta, okay, so for theta is minus 12, minus 4, and 12. So theta is the middle one, okay? So theta is the middle one, which is minus 12, minus 4, and minus 12. So we follow this equation. So I repeat again, okay? I repeat again. Y is this one, okay? Y k plus 1. So if k equal to 0, so y 1. K equal to 1, y 2. K equal to 2, y 3. So this one is y1, y2, and y3. So you take directly from the data here, y1, y2, and y3, because the sequence, we follow the sequence, okay? K equal to 0, K equal to 1, K equal to 2, and y actually is yk plus 1. Okay, so when k is equal to 0, it become y1, k equal to 1, y become y2, k equal to 2, y equal to 3. Okay, so we have to follow this one, 2, 3, and 4. So 4 minus 12 and minus 4 will be the definitions for vector y. And then for vector theta, we have input and output, which is here. Okay, so it's a yk and uk. Okay, so for y there is a negative, for u there is a positive. Okay, so we take from here. So minus 12, minus 4, 12. Okay, so this one y1 minus 12 minus positive 12 minus 12, which is here, minus positive 4 minus 4, and minus minus 12 positive 12. So we get the first column. And then for the second column is the B1 UK. So it's a positive. So directly you can take from the input, okay, which is 1, minus 1, and minus 1. 1, minus 1, and minus 1, you insert directly to the second column, okay. So that's why we already defined the Y matrix, okay, theta matrix, which is this one is a 3 by 1, this one is a 3 by 2, okay, and this one is a 2 by 1 matrices. So we're going to estimate the beta, okay. So beta is equal to theta transpose theta multiplied together inverse, then multiplied with theta transpose y, okay. So from here, theta, this is theta, minus 12, minus 4, 12, 1, minus 1, minus 1. So for theta transpose is interchange between the row and column. So this is row, become column, minus 12, 1. Minus 4, minus 1 is row, become column, minus 4 minus 1. 12 minus 1 is the column, sorry, is the row, convert to column, 12 minus 1. So it will become minus 12, minus 4, 12, 1, minus 1, minus 1. That is the theta transpose. And this one will be multiplied together. Okay, will be multiplied together, and it will give you a 2 by 2 matrix because theta transpose is 2 by 2 by 3. And this one, theta is 3 by 2, the size, okay? So this one is the same, front and end, so it will give you 2 by 2, which is 304 minus 20, minus 20, and 3 by using a calculator. Then after you get this, you do the inverse, okay? So theta transpose theta, okay, is 304 minus 20 minus 23. So in order to apply theta inverse, okay, manually, okay, so listen very carefully, change the seat between 3 and 304. 3 go here, 304 here. And then negative the perpendicular. Negative, negative 20, positive 20, negative, negative 20, positive 20. Okay, that's why you get this answer. Then you can factorize 1 over 512, okay, in order to get the final answer. And then theta transpose y. Okay, theta transpose y is this one, theta transpose. So theta transpose y is this one is a 2 by 3 matrices, and y, which is here, is a 3 by 1. So you will get an answer of 2 by 1, okay, which is the minus 48 and 20 using a calculator. And finally, you multiply this matrix with the theta, theta, y, then you get the value of A1, which is equal to 0.5, and B1, which is equal to 10. Okay. So this is the model structure, first order, and then this is the final model with the estimated parameter, which is B1 equal to 10 and A1 equal to 0.5 as shown here. Okay, and using the difference equation, which is shown as previously. So we know the sequence is 1, 2, 3, 4, and then the input is U, and the output is Y. Okay, so the estimated output is using the answer that we get, which is 10 and 0.5. Then we can find the error between the y and y cap. Okay, so error is between the y, okay, and minus y cap. Okay, the modulus. Okay, so you can estimate the y, which is shown here. Okay, and then fill out the empty spaces as shown. So this one is another example, okay, for the given process model is past year questions, where this is the process model in the form of discrete form is the first order system, okay, and the data given is k is equal to 1, 2, 3, 4, u and y is given, okay. So find the simple least square think this one is okay. Find the simple least square by rewriting the model in the form of y k plus 1, which is equal to minus a y k plus b1 u of k in the matrix form of y theta beta. Okay. So again, we have to construct the matrix y. Okay. So in this case, we use this yk plus 1. Okay. So yk plus 1, we start from the here. Okay. Y k plus 1. So let's k is equal to 1. Y 2. Okay. K is equal to 2. Y 3. K is equal to 3. Y 4. So in this case, when k equal to 1, y2 is 5. Okay, here. And then y3, 0. And then y4 is minus 2. So we base on the sequence here, k, 2, 3, and 4. So we already construct the matrix Y, which is 3 by 1. And then for matrix theta have 2. Okay. If you look here, minus A1 at YK, positive B1 at UK. So again, we use the sequence as shown. Okay. So Y1, okay, Y1, because K equal to 1. So Y1, negative Y1, because we have a negative here. So Y1 is minus 4, minus 4, positive 4. Then K equal to 2 is Y2. Okay, Y2 is here, minus positive 5, minus 5. Then K equal to 3, minus Y3. So minus 0 is 0. Okay. Then the next one will be B1 UK. So B1 UK, we follow here, K equal to 1. Okay, so it will be U1. Okay, so U1 is 1. K equal to 2, U2, 1. K equal to 3, U3, minus 1. Okay, minus 1. So we construct the theta matrix. And then beta, leave it as A1 and B1. Okay, so find the transpose. So if theta is equal to 4 minus 5, 0, 1, 1 minus 1. So the theta transpose is interchange between row and column. So this one will become 4, 1, minus 5, 1, 0, minus 1. Okay, that is transpose. Okay, then use the formula. Okay, so you have to remember this formula. In the final exam, it's not given. Okay, so estimated beta is equal to theta transpose theta inverse multiplied by theta transpose multiplied by y. Then do the calculations using the calculator. Okay, then you get the final answer here, right? So the final answer will use we use this, okay, as the what do you call that, as the estimated y. Okay, so k is equal to 1, y2 is equal to minus 0.55 multiplied by minus 4. okay, plus 2.5 multiplied by 1, you got 4.7. So you insert the estimated 4.7 here. K equal to 2, okay, use the E1 that we get, okay, and then the B1 multiplied with the data given, then you get minus 0.25, which is here, okay. Then for Y4, same as well, so you get minus 2.5. Then the error is mean squared error, okay. So mean squared error meaning that you multiply using the formula of mean squared error. So you get the average is about 0.134 for the calculation, which is good and can be further improved. So I leave this least square for you to try after the class, okay, which is answer given here, and you have to work out the solutions, okay, using the two examples shown previously. Right, so it's almost 10 o'clock, so we stop for a while for rest, about 15 minutes. Is it okay?
Okay, Prof.
So rehat 15 minit, okay, then we continue at 10:15. Hello, testing 1 2 3 1. Dengar?
Dengar, Prof.
Okay, we continue. Okay, right. So
Okay, Prof. Okay.
continue to slide 45, which is the overview of the practical system ID. So the ideal case where the least square technique that we learned previously works great, okay, but the technique begins to break down under some non-linearities, okay, quantizations and noise, okay. So how do we recover good fitting? Okay, so we have to do some modifications on that least square identifier algorithms by applying a filtered least square and averaging. Okay, so this is two kind of amendments that we did on the least square estimator. Okay, by improving the identifications under noise and quantizations, we applied a filtered least square and then we averaging it. Okay, in time domain and frequency domains, where lots of data will have during the improvement of this technique. So the block diagram will we add some more between the A to D, D to A, and identifier algorithm where we apply filter, okay, F of Q, okay, at the input and at the output, right? And this all done using computer programming, okay? Because we cannot do it manually. So manually, usually length of data 4 or 5 is okay, but when more than 5, so the calculation will be longer, okay? Manually, it will go to about maybe 10 pages, okay? So it's not practical to do it manually, so if we have to do it using computer programming, okay, and the identifier algorithm to find the model. Okay. So why we do this? Why we do the filter? Due to the fact that there is a non-linearity factors, due to the fact that we have a quantization problem, due to the fact that we have a very noisy data where signal to noise ratio is very low, okay, very low SNR. So that's why we introduce a filtered least square at the input. If you have input data U, output data Y, so the transfer function selection model will become Y over U. And then if we want to apply the filter, so we just put like a sine wave symbol at the top of U and Y. That is the sense of filter. Okay, so estimated filtered transfer functions will become filtered Y, filtered U, which is equal to FQ, YQ divided by input, which is equivalent to Y over U. So what do we use as the filter? So iterative algorithm. First, we perform the least square identifications. Then we use the obtained denominator and 1 for numerator. Okay, and then filter the input output. Then perform the least square identification on the filtered data, not on the non-filtered. Previously, in the example 1, example 2, and example 3 homework, okay, self-homework, we are using non-filtered data. But in this case, we will go on the least square identification 2 times. First, least square identification on the non-filtered data, and number 4, least square identification on the filtered data, meaning that you have to do the calculation twice. Okay, so use the obtained denominator and 1 for numerator, then we repeat 3, 4, 3 to 5 until the converged value of the parameters is achieved. Okay, so generalized least square is something like this. We consider the model, okay, as Y, Okay, then we rearrange the equations, then we postulate a filter and multiply both sides by the filter, and then the equation will become filtered equations. Then Fy and Fu as the filtered input output in the equation of y equal to F filtered multiplied by y and U filtered multiplied by the input U. Thus, the generalized least square, we call it generalized least square. So in generalized least square, we apply the filter. So the estimated will become beta cap as usual, theta transpose theta inverse, theta transpose y, which will be biased. And we analyze it using the autoregressive model. Okay, then we obtain the filter and for input and for the output. Okay, SYF and UF. Then we perform again to obtain the estimated generalized least square. Okay, so we have to do the looping, okay, until it converges. And this is required computer programming. So we consider a simple case here where B over A is the ARX model. Okay, zeta is the noise, input is U, output is Y, B is the polynomial, A is the polynomial. So using a generalized least square, we filtered both sides with F, okay, and then we obtain the equation 1, which is Y K filtered and U K filtered. Okay, so this is examples, okay, to describe how we apply the filter. Okay, you are given xk, which is equal to the first order order structure. Okay, multiplied by u. U is input, y is output, and y is equal to xk plus zeta k. Zeta k is the zero mean discrete white noise sequence. Okay, so using the data given here, okay, so estimate the data for A and B, then estimate the parameter A and B after one step of generalized least square. Procedures with initial conditions. Okay, so in filtered least square, so we have initial conditions, which is YF0 is equal to 29.97 and UF0 is equal to minus 1.87. Okay, so data is given, sequence K 1, 2, 3, 4, and U is minus 1, 1, 1, 1, and YK is minus 16, 0, 9, 3. So we will do the least square estimate based on non-filtered data, which is here. And then we have to generate one step using the generalized least square, using the filtered initially given by 29.97 and 1 minus 1.7. The true value is 0.5 and B equal to 8. A is equal to 0.5 and B is equal to 8. Okay, so let's go to the whiteboard. Okay, so this is whiteboard. Right, so again, we are applying what you call this, the difference equations. Y k plus 1 equal to minus a y k plus b u k plus the noise part. Okay, this is the noise part, discrete white noise. So remember this equation, y is equal to sine beta plus e. So we have to perform the y first, okay? So as usual, we start k is equal to 1, okay, for y. So y k plus 1 is equal to 2, okay? So we follow these equations. Okay, y2 is here, which is 0. Okay. Then k is equal to 2, y 3. So y3 from the data is, this is 1, this is 2, this is 3, which is 9. Okay. Then k is equal to 3, y is equal to 4. So y4 is 3 here. Okay. So we already obtained the matrix y, okay, which is y is equal to 0, 9, 3. This is, the size is 3 by 1 matrices. Then we construct the matrix theta, okay, matrix theta, which is this part. Matrix theta is combination of y minus y and u. Okay, y minus, because the equation is minus there, minus ayk plus buk. So again, we construct for matrix theta, okay, k equal to 1, okay, y1, okay, so minus y1, because the equation is minus, so y1 is minus 16, so minus 16 plus 16, okay. And then k is equal to 2, okay, y2. y2 is here, 0, minus 0 is 0. And then k is equal to 3, y3 minus. So minus y3 is 9. So minus positive 9 becomes minus 9. So that's why you get 16, 0, and minus 9. Again, for the second column, which is for UK, okay, for UK, k is equal to 1, u1 is minus 1, yeah, okay, k is equal to 2, u2 is equal to positive 1, and k is equal to 3, u3 is equal to 1. Okay, so minus 1, 1, 1, insert inside the column. Okay, then beta is the estimated parameters of the transfer functions. Then we apply beta cap. Okay, remember this formula. Formula is not given. Please remember beta cap or estimated beta is equal to theta transpose theta multiplied together inverse 1. Okay, multiplied by theta transpose multiplied by y. Okay, so find the product of theta transpose theta, inverse theta transpose theta, theta transpose y, then multiply together. So you obtain the value of A is equal to 0.56 and B is equal to 8.72. Okay. Okay. Right. So we finish on the simple least square, and we need to use this A in our next calculations, which is estimated A or A cap is equal to 0.56. So the generalized least square in filtered form, as we learned before, is YF, Y filtered is equal to Y divided by 1 plus A cap, Z minus 1. And for the input, UFK is equal to UK divided by 1 plus A cap. Okay, so it is using A cap value. So this value is very important. Once you wrong here, then you bring the calculation, the A cap, the wrong A cap in the second part. So it will destroy all the solution and you get a wrong answer. So you have to be careful on the first part. So the A, 0.56, the A cap, okay, is the least square estimator of the parameter A that we have to use in the substitutions in our formula, which is here, okay, YFK, K plus 1, okay, is equal to minus, okay, minus A, Y filtered plus B, U filtered, and the error part to compensate the value. Okay, so we calculate the y of k now. Okay, y of k 1, okay, which is equal to minus e cap y f k minus 1 plus y k, right? And then so the initial conditions is given by 29.97. Okay, so y f1 is minus 16 from the data, okay, minus 16, then minus the A value, A cap, okay, the A cap, and then filtered 29.97, okay, you get minus 32.78. Use these equations, right? So minus 16 is y1, positive, okay, y1 positive, so minus 16 there, okay, minus A cap 0.56 from the value here that we get in the first part, then multiplied with the initial condition y filter 0, okay, so you obtain minus 32.78. Then the next step is yf2, okay, 0 is the y2, then y2, okay, y2 minus A cap 0.56 multiplied with the yf1. yf1 is minus 32.78. So you bring this value inside the second step. You get 18.356. Then continue yf3. 9 is from y3. y3 here. Okay. Insert the value y3 minus 0 A cap minus 0.56. 18.356. You go here. Okay. Then you get minus 1.279. Then finally, yf4 is 3. Okay, 3 is from the table. Y4 here. Minus A cap. Okay, E estimator 0.56 minus 1.279, which is from here, the value. Then you get 3.716. Okay, this is for the output. For the input, so the formula using is U of k minus A cap, U filtered plus UK. Initial conditions minus 1.87. So UF1, okay, is minus 1. Minus 1 is from U1. So U1 is here, okay, minus 1. So minus 1, okay, plus 0.56 A cap multiplied by the UF0 minus 1.87. So 0.049. Okay. This is U2. U2 from the data is 1. Okay. So 1 minus A cap 0.56, then multiplied by 0.049 from the first calculations. Now you get 0.97. Then UF3, 1 is U3 from the data, minus A cap 0.56 multiplied by 0.9724 from the UF2, bring it down. Then UF4 is 1, which is from the data, minus A cap multiplied by 0.45 from UF3, then you get the UF4, 0.75. So you have 4 Y filtered and 4 input filtered. Okay, so you arrange like this. Okay, so sequence K 1, 2, 3, 4. This is UK, the previous one. YK, the unfiltered data. And you have the filtered data for U, and you have a filtered data for Y. Okay, as you calculate previously. Okay, and then you do the least square again. Okay, least square again for the filtered data. Do not apply on the non-filtered data because non-filtered data is already done in the part 1. So in the part 2 is you apply on the filtered data, which is UFK and YFK. So you find the YF, you find the theta F, then you multiply, then you inverse, and then you multiply with the YF, and finally you use the estimated least square, okay, which is you will get the value, okay, of the A filtered, okay, A filtered and B filtered, okay, which is 0.54 and 8.5, okay, which is an improvement from the previous simple least square estimate. Although generalized least square solution after one iteration is still biased, further iteration would be unbiased when we estimate the beta. Okay. Then there is one more examples, which is shown here, where more similar but different data. Okay. You have unfiltered data, UK and YK, using a simple least square estimate and estimated one-step generalized least square with the initial conditions YF0 6.22 and UF0 minus 2.0. So the answer is given as here, but you have to do the solutions after the class. Okay, after the class, maybe exercise for tonight and ready for the tomorrow test. Okay. Right, so that is chapter 4 slides. Okay, any questions? Ada soalan?
Prof,
Ya.
basically from beta we get A and B kan?
Ya.
Kita tak guna B punya value lah, only A.
Untuk filtered, untuk kira filtered, kita tak pakai beta cap, B cap. Okay, so kalau you lihat pada formula, let me share again. Okay, kita tak pakai beta, so you boleh lihat sini dia banyak kan, 0.56, 0.56 kan. So kita gunakan A cap. Okay, so beta tu nanti kita banyak guna dekat masa kita kira least square filtered tu nanti. Okay, so dalam filter ni tak pakai B cap, tak pakai. So, kita pakai E. Jadi dia cuma dia generalizekan lagi least square estimate itu. Did I answer your question?
Yes, Prof. Thank you.
So yang homework ni kena buat. Nanti buat dan comparekan dengan jawapan yang saya berikan. Sebab besok adalah test for chapter 4, test 2. Besok punya kelas kita mula pukul 2 petang. Sebab pagi saya ada kelas lain di Penang. Okay, so besok pagi kita, besok hari Ahad kita mula pukul 2 petang. Okay, ada lecture sikit dan kita follow dengan test. Any more questions? Ada soalan nak tanya? Jangan malu-malu. Boleh faham tak chapter hari ni? Sebab besok kita ada test on this chapter, chapter 4.
Nanti Prof bagi video ni kan?
Bagi.
Revision.
Video bagi. Ha. Video bagi. Any question? Apa pun nak tanya? Generalized least square, chapter 4, assignment. Exams, exams dah siap, dah di komen, dah vet oleh panel. So dia ada 4 soalan. Okay, ada 4 soalan, jawab semua soalan. So tak ada pilihan. Masa online nanti macam test one lah. Awak kena on video. Okay. Dan awak kena sediakan A4 paper. Soalan kita akan letak test 2 dah letak lah. Ya, cuma awak tak nampak. Kemudian final exam pun sama, kita akan letak di e-learning dan awak kena upload. Nanti ada password, kita bagi password. Okay. Any question?
Hello, Prof.
Yeah.
Regarding assignment, so we are having the problem to measure our output actually because we don't have the access to oscilloscope.
Okay.
Mm,
Pakai apa? Arduino.
yeah, Arduino.
Okay. Lagi, Daniel? Is there any idea? Can you interface the Arduino dengan laptop you? Boleh nampak tak?
Boleh tapi kena belum ni lagi lah.
Cuba lah. Pelajar dia dapat display from the Arduino. Dia boleh display ke.
Okay.
Sebenarnya assignment ni banyak saya nak tengok creativity je. Orang punya dare to give idea. Sebab dah masters level kan, kita tak macam undergraduate level, kita kena ikut tak. Yang ini dia more freedom. Kalau awak ada idea, brave to give idea, dare to give idea in discussions. Okay, so I will evaluate that one lah, more on the creativity, your imagination, maknanya lain daripada yang lain. Itu yang example slide yang saya bagi itu is just an example. Okay, so you can follow, but not necessary you have to follow them. If you have any better idea, any good idea, put it on the slide. Okay, so I will listen to your presentation next Saturday, starting from 10 a.m. until 12 p.m. So each person will present 20 minutes. I will give the timetables very soon. Okay, then I comment. Okay, so I comment, you take note, then you improve your slide. Then after you improve your slide, you masukkan dia ke dalam e-learning. Okay, upload by Sunday. Okay. Maknanya next week tu Saturday Sunday tu Saturday tu sebenarnya tak ada kelas, tapi saya kena buat juga sebab nak evaluate assignment. Dia bagi 3 kali jumpa je kan. So macam tak berapa sempat lah. Tapi by 1st of February maknanya dah tak ada lagi load yang saya bagi pada awak lah. Sebab final exam is on the 20th of February. Tentative 20th of February. So your sections will be sama dengan perdana lah. Perdana ada 9. Kat sini ada berapa 7 tak salah. Ada 7 9 tambah 7 ada 16 orang. 20 Februari. 20 Februari tu hari apa? 20 Februari adalah hari Sabtu. Kan? Awak tak kerja kan? So bolehlah buat exam sekarang. Tapi kita akan bincang lah from time to time. If you have any answer, you can share in the WhatsApp. I will try to answer the questions. Okay. Ada soalan? Kalau tak ada soalan, can I move to chapter 5A? Boleh?
Okay, Prof, boleh.
Okay, boleh Chapter 5A Okay, this is chapter 5A. Chapter 5A is the case study for the system ID where we where we apply all the chapter 1, 2, 3, and 4 into a case study. So the first case study that we are going to see is the hot air blower system. So where do we apply hot air blower system? Can somebody from the industry give an output? Sivananta? Sivananta?
Yes, Doctor.
Where we apply hot air blower system?
Yes.
Where about? Kat mana? Tanya je lah, mana tahu. No idea. Tak tahu. Nur Fariza?
The production area.
Huh? Sorry?
In the production areas.
Connection areas?
Production.
Sorry, akan...
Production plant.
Oh, kat mana tu? Dalam area mana tu?
Dalam mechanical plant room.
Okay. Nur Fariza? Where do you apply a hot air blower system? Nur Fariza, datang tu.
Yes, Doctor.
Where do we apply hot air blower system? Kalau musim hujan, baju tak kering, kat mana kita buat?
Laundry.
Dryer, tumbler kan? Dryer kan? Musim hujan, jemur baju tak kering kan? Kita pakai tumble dryer. Tumble dryer kan dia ada setting kan? 20 minutes, 40 minutes, 30 minutes, and then dia ikut baju cotton ke, wool ke, atau polyester. So all these temperature variations, we are using a hot air blower system. Okay, that is the example yang paling mudah. Okay, so this is the what do you call that? Prototype model. Okay, for the hot air blower system. Okay, so the descriptions is for these presentations, we'll touch on the system descriptions, setting up data for analysis, pre-processing data, estimating non-parametric and parametric models, analyzing the estimated model, estimating models with a prescribed structure, validating the estimated model to experimental output, comparing estimated models and additional information. So we are going to apply the system ID toolbox in MATLAB. I hope you already installed it to develop and to analyze a simple model from a real laboratory process data. So start with the small descriptions of the process. We import the data to the toolbox and the pre-processed conditions. Then we estimate the parametric and the non-parametric models. After that, we identify the estimated model and validate the models to the actual output data from the experiment. So we are using a hair dryer data, okay, which is in the books, Leonard Jung books, okay. So this process works as follow, where air is fanned through a tube and then heated at the inlet, okay. The air temperature is measured by a thermocouple or thermistor at the outlet. Okay. The input data is U, which is the power over the heating device. Okay. Which consists of a mesh of wire, a resistor wire. Then the output will be the voltage from the thermocouple or thermistor measurements. Okay. So this is the trainer where the data has been captured. Okay, so the air will flow. Sorry, the air will flow. Okay, to here. Okay, where this is the where the fan. Okay, the fan actually is the motor that rotating, and the mesh wire, mesh resistor wire. Okay, which is inside this box as well. So the fan will rotate and suck the air from outside. Okay, and then we will go to the mesh wire at this device, which is heated. Okay, warna merah, and the fan will push the hot air towards the exhaust here. Okay, and there is a thermistor which will be located near the exhaust to measure the output temperature. And then this output temperature will go to the system, to the controller. Okay, so we have two types of controller. One is a continuous control, which is a PID. And then a two-step control, which is a on-off controller. Okay, so this system have two configurations. If open loop, okay, so open loop, it is a first order system. Okay, if closed loop, so it will be a second order system. Okay. So this is the real system in the laboratory where we capture the data. Okay. Then in order to use MATLAB, we have to, first we have to, there is two ways. One is by MATLAB command, syntax command, which is using a code. We wrote the code, we write the code on the MATLAB double prompt. Okay, by typing load dryer2, because dryer2 is the data that given by the MATLAB for hot air blower system testing. Then this data consists of Y2, which is 1000 output, and U2, which is consist of 1000 input data. Okay, and the input was the binary random binary sequence, or PRBS, that switch from one level to another level with probability of 0.2. Sampling interval is at 0.08 seconds. So the next step is to set up the data as a ID data object, which is using this command. Okay, dry where ID data is equal to Y2 output data, U2 input data, and 0.08, which is the sampling time. So to get the information of the data, we just type dry MATLAB, okay? Then it will show you the data of U and Y with sampling interval 0.08. And then if you use a command get dry, okay? So it will show you the data in the numerical form, okay, with the unit, okay, and with the sampling time as well. So for better bookkeeping, kita biasanya kena labelkan input data tu sebagai maklumat. For input is power in watt, temperature output is temperature in Celsius. Okay, unit time is second. Okay. Then we can shortlist the data. Since we have 1000 data, so if we plot the data from 1 to 1000, it will make your screen more, what do you call that? Saturated. So we just plot the first 300 data points by using a command, ZE is equal to dry 1 to 300, then it will show you the data by plotting. Okay, by plotting is it plot ZE 200 to 300 data, So it will give you something like this. Okay, so this is what we call that as a temperature data, which is the output and the input in watt. Okay, you can see that it is like a random binary sequence, and the output try to follow the input as good as possible. Okay. Then from the data, you can see that there is a calibration problem. You can see that this one, the data is not start from 0. Okay, so there is an offset in this data, so we have to remove the offset by using the command, okay, dtrend. So we use the command dtrend, okay, dtrend the data ZE, then we plot it, then you can see that the data now is better compared to the previous one where it start from 0 and start from 0. Okay, this is what we call as pre-processing data. Okay, so before you start to analyze the data, we do the pre-processing. Kita bersihkan data tu lah. Macam kita beli ikan, kita bersihkan perut dia, kita bersihkan darah dia, the unnecessary punya items, and then baru kita masak. Okay, so sama lah macam sistem ID, kita kena ada pre-process. Kita kena removekan DC offset first, detrend, outliers, then the data is clean, then kita boleh analyze to get the mathematical model. So we test using the non-parametric method, impulse, to see the behavior of the data. Okay, so this one, it shows that the data is almost like what do you call that, as a closed loop pattern. Okay, the second order, if you see, goes up and it goes down. Okay, like a decaying sine wave in chapter 2. Okay, I already described it in the chapter 2. Okay, so this is the impulse where we can see that majority of it in the 0 baseline. Okay, and the changing is on the upper baseline. And then we estimate the parameters. Instead of least square, we have another method, which is the prediction error method. So I didn't discuss this because I want to reduce the scope as small as possible. Okay, because we are in the online version, so it's very difficult to show high-level mathematics. So I hope you can familiarize with the simple least square and generalized least square. Okay, and then we can produce the state space model using the prediction error method. Okay, for the parameter estimations. So state space model also not included in our scope, so I ignore it. I focus on the transfer function model. Then we can analyze the Bode plot. Okay, so the Bode plot is shown here. So is from the observations, you can see that it is a second order system. Okay, kalau you tengok dia punya slope dia ni, berapa decibel dia. Kalau dia minus 20 decibel per decade, maknanya dia adalah first order. Kalau dia adalah minus 40 decibel per decade slope-nya, maka dia adalah second order system. Okay. And look at the phase. Okay, so usually kalau dia 0 to minus 90 degrees, dia adalah first order. Kalau dia 0 to minus 180, so dia adalah second order. But this one is, dia terjunam terus daripada minus 180 ni, dia terjunam terus ke dalam ke bawah, maknanya dia adalah second order with time delay. Okay, ada time delay in the transfer function. Boleh So Nyquist is another alternative to represent the non-parametric in frequency domain, but this one is not popular compared to the Bode plot. So I will ignore it. So for step, you can see that this is the step functions. So you can see from here, there is a time delay in the system. Kalau kita lihat di sini 0. So after 0 tu dia ada macam ada lambat sikit baru dia naik kan. So ini kita panggil dia sebagai time delay. And it give you about the second order response. Right? I think it's about almost undamp or underdamp, something like that, in the response of the step. Then we applied for the ARX model, okay, for this data with assumption of the model have 2 poles, 1, 0, and 3 delays, okay. So it will give you the B polynomials as the upper or numerator, and the A polynomials for the, what do you call that? The denominator, okay. So this is the ARX model, okay. So kena tahu ARX model in chapter 3 that we learned before, okay. And then we use it to ARX data. Then we use the least square, which is inside the system ID toolbox. Then you can see that ada 2 line di sini. Satu adalah blue line, satu lagi adalah black line. So black line ni adalah real measurement. Okay, is a real measurement from the real data, the black one, and the blue one is the ARX model that fit the data, 88.73%, meaning that nearly 90% can be further improved. Okay, but so far the ARX model blue line try to follow the black line, the real data as good as possible. Okay, so maknanya okay, very good jugalah. Tapi dia punya ni adalah 88.73, kalau round up 89%, okay lah, macam 90% juga, okay, which is the agreement is very good. Okay, so we compare the model via state space and model via parametrics. Okay, you can see that model 1 adalah, model 1 tadi apa? Model 1 adalah state space, so model 2 adalah ARX model. Okay, you can see that the fitting is about the same, 88.73 using the ARX model. 88.43 is the state space model. Okay, so tak banyak beza. Dan kedua-dua model, estimated model ini mengikut, the agreement is very good with the real data, which is on the black one. Okay. And then we can see the mapping for the poles and zero for ARX model. So kita ada 3 poles, okay. Ada 3 poles, ada 3 poles, 3 zeros, ARX 2 to 1, 2 to 3, okay. 2 poles and 1 zeros, okay. And compare with the state space model, which is 3 poles and 2 zeros. Okay, you can see that the mapping is about the same. So the circle one is the unit circles that indicate the stability and the minimum phase and the non-minimum phase part. Okay, so this is the zoom one and the board as well for the model 1 and model 2 compare with the real part. Okay, and all the legend for labeling and so on. Okay, so I will stop here for the kita rehat sebentar 2 jam untuk you makan tengah hari dan kita sambung balik pukul 2. Boleh tak?
Boleh, Prof.
Rehat makan tengah hari, okay, dan kita sambung balik pukul 2. So make sure you ada MATLAB and System ID Toolbox, okay, untuk kita pergi kepada chapter 5B dan 5C, okay. Kita rehat dan masuk balik dalam pukul 2. Okay, boleh?
Boleh, Prof.
Okay, saya end the session then I will open the session, okay, at 2 o'clock.